A chunking bug truncated blocks and reused existing hashes, so two different blocks produced the same SHA-256. The deduplication layer assumed identical hashes meant identical content, returning garbage for unrelated files. Here's exactly why. Let's start with the basics of content-addressable storage. Welcome to TheCodeForge. Before we dig into that production issue, let's cover Design Dropbox. Dropbox's design is a content-addressable file storage system where each file is identified by the cryptographic hash, SHA-256, of its contents, not its name or path. This allows deduplication across users, saving storage costs. The system splits files into 4 MB blocks, each hashed independently. The block store is a giant map from hash to data. The Metadata Service tracks file hierarchy and block references. Dropbox uses a pull-based sync model. The client watches the local file system for changes, chunks files into blocks, computes SHA-256 hashes, and uploads missing blocks to the block store. Then it sends a metadata update to the server. The server validates the block hashes exist, commits the change, and appends to a changelog. Other clients poll for changes via long polling. Every file is split into 4 MB blocks. The last block may be smaller and is merged with the previous block if under 1 MB. Each block gets a SHA-256 hash. The block store is content addressable. Blocks are stored at paths like /blocks/#0, 2/#2, 4/#. If the hash already exists, the upload is skipped, achieving deduplication. Here's the Java implementation of the block chunker. It splits the file into 4 MB blocks, computes SHA-256 hash for each, and merges the last small block with the previous one. This is the core of content-addressable storage. The metadata service is the single source of truth for file hierarchy. Each user's file tree is stored in a relational database, sharded by userid. The tree uses an adjacency list. A changelog table records every change, enabling efficient delta sync. Read operations are served from replicas, writes go to the primary. Here's the simplified schema for the metadata service. The files table stores the file tree, and the file changelog table records every change for delta sync. The changelog is indexed by userid and changed for efficient polling. When two clients edit the same file concurrently, the first upload wins. The second is saved as a conflict copy with a suffix like conflicted copy. The server uses a version counter on each file entry. If the version in the update doesn't match the current server version, it's a conflict. Conflict copies only add metadata rows, not block storage, because deduplication already stores the blocks. Dropbox scales to 500 plus PB of user data and 700 million files uploaded per day. Metadata is sharded across 100 plus MySQL shards. The block store is a custom object store called Magic Pocket, built on JBOD servers. The notification service handles 500K long pole connections per pod, using a consistent hash ring to root users. This YAML snippet shows the deployment scale. The notification service has 200 replicas, each handling 500K connections. Metadata is sharded across 128 MySQL shards with primary and replicas. The block store uses 10,000 plus servers with erasure coding. The client population of 500 M active users generates 600 M poll requests per second. The client sync engine runs as a background process. It uses OS file system event APIs to detect changes. After a 200 ms quiet period to batch rapid edits, it computes the file tree diff, chunks changed files, and uploads blocks in parallel, up to 10 concurrent connections. Each block upload includes the SHA-256 hash. After all blocks are uploaded, it sends a metadata update. Here's a simplified Python version of the client upload pipeline. It waits 200 ms after a file change, computes the SHA-256 hash, checks if the block already exists remotely, and if not, uploads blocks in parallel using a thread pool. Finally, it updates the metadata server with the new file hash. Before writing code, define system requirements. Functional requirements include upload, download, share, and sync across devices. Non-functional requirements include 99.999% availability, 5 minutes downtime per year, and 11.9's durability. ACID properties ensure metadata operations don't corrupt data. Write requirements as executable assertions and test them. This Python class encodes system requirements as code. It defines functional and non-functional requirements and validates them. This makes requirements traceable and testable, preventing fuzzy specifications that lead to production incidents. Capacity estimation forces you to think about numbers before building. With 500 million total users and 100 million daily actives, each storing 200 files averaging 100 KB, you get 100 billion files and 10 PB of storage. Peak bandwidth at 1 million connections per minute is 1.67 GB. These numbers inform infrastructure choices. This Python data class calculates storage and bandwidth estimates. It outputs 9.31 PB for 100 billion files and 1.67 Gbps peak bandwidth. These estimates help choose the right database, storage tier, and bandwidth package. The high-level design includes 3 services: upload, metadata, and sync. The client gets a presigned URL from the upload service and uploads directly to simple storage service. The metadata service tracks file names, sizes, and parent directories. The sync service triggers notifications to other devices. This keeps services stateless and scalable. This Flask app generates presigned URLs for direct simple storage service uploads and downloads. The client sends file metadata, gets a URL, and uploads directly to simple storage service, avoiding server-side proxying. This pattern keeps the application server stateless and scalable. This is the same issue we highlighted at the start. Here's exactly why that happened. A bug in the chunking library truncated blocks and reused existing hashes, so 2 different blocks produced the same SHA-256. The deduplication layer assumed identical hashes meant identical content, so it returned the wrong block to users, causing file corruption. The fix added a block-level CRC checksum stored alongside the hash. On every read, the system verifies the first few bytes before returning cached blocks. This ensures that even if a hash collision occurs, the integrity check catches it. A background integrity check service periodically verifies all blocks against their hashes. Never assume deduplication is lossless without an integrity check layer. Always verify block content on read for mission-critical data. Add a block-level CRC checksum stored alongside the hash for double verification. Using push notifications instead of polling can overwhelm the server with connection overhead. Use long polling or WebSockets only for lightweight notifications. Keep the metadata service stateless and have clients pull changes based on a changelog cursor. If a client is offline for months, the changelog may have millions of entries. Scanning them all causes performance issues. Implement changelog archival, move entries older than 30 days to cold storage, and serve a full file tree snapshot for stale clients. The article correctly notes SHA-256 collisions are astronomically unlikely, but in practice, the risk is not from random chance but from implementation bugs, as in the 2016 incident, or from using truncated hashes. Always use the full 256-bit hash and never truncate it for deduplication. The article mentions adding a CRC check after the collision incident. Here's a concrete implementation that verifies a stored CRC before returning block data, preventing silent corruption from hash collisions. The article recommends content-defined chunking, CDC, for large edited files, but doesn't mention that CDC is CPU-intensive and can cause variable block sizes. In production, use a rolling hash like rsync, weak checksum, or ttmath. uint to find chunk boundaries and set minimum-maximum block sizes to avoid pathological cases. Here are common debug commands. Use Dropbox status to check file status. Grep the error log for upload failures. Check metadata replication lag with curl. Test block store connectivity with netcat. These commands help diagnose sync issues. Let's run through some common interview questions. How would you design a file sync service like Dropbox? Use block-level chunking, SHA-256 dedup, sharded MySQL metadata, changelog for delta sync, long polling for notifications. How to handle a user with 1 million files syncing slowly? Optimize metadata queries with indexes, serve full snapshot for stale clients, parallelize uploads, use caching. Explain eventual consistency in Dropbox and mitigations. Write to primary, read from primary for same user, use changelog as source of truth, display syncing indicator. And a few frequently asked questions. Why 4 MB block size? Sweet spot. Small enough for parallel uploads and efficient delta sync, large enough to keep metadata overhead low. How does sharing work across shards? Shared folder owned by creator's shard, members poll owner's shard for changes. No cross-shard transactions. What happens when a client comes back after months offline? Server detects large gap and serves full file tree snapshot instead of replaying changelog. To recap, Dropbox uses block-level chunking with SHA-256 deduplication to save storage and bandwidth. The Metadata Service uses a sharded MySQL with changelog for efficient delta sync. Conflict resolution creates conflict copies rather than losing data. And always verify block integrity, CRC, even with strong hashing. The production incident taught this the hard way. Ready to go deeper? Up next, design Slack, then design a rate limiter, then design a notification system. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.